Hey guys, Miss Peterson here, and welcome to a chemistry lecture on the history of the atom. In this lecture, we're going to be going through how our current atomic theory came to be, starting with the first atomic theory of 1808 and leading to the quantum theory of today. We'll really go through how to understand the experiments the scientists did that led to our change in understanding of all of the matter that makes up our universe. So let's get started. So the first atomic theory is credited to John Dalton back in 1808. He ran through some simple experiments and saw that compounds always break down in the same whole number ratios. Okay? Basically, water will always break down into 2 hydrogens and 1 oxygen. So he came up with the idea that all matter is made of tiny, indivisible particles called atoms. Now, the word atoms was not new. We had the word atoms from a long time ago. The Greek word atomos, meaning indivisible. And he said that the atoms of a specific element are identical in mass, size, and other properties, that they cannot be created nor destroyed nor divided, that they combine with each other in fixed whole number ratios to form compounds, and that they can be rearranged, combined, or separated in chemical reactions. Now, really great on those last two. Totally had the idea of chemical reactions. He had the idea of conservation of matter. The only thing he didn't have is he thought that the atoms were the smallest thing ever in existence, and that there was nothing smaller than him. And it took some work of some other really smart scientists till we discovered what was actually inside those atoms. Now, the first one was J.J. Thompson, and he experimented with something called cathode rays. We're going to look at a simulation of those cathode rays in a minute. And I want you to ask yourself the following. Does the cathode ray have a positive or negative charge? And do different materials create different rays or similar rays? And what conclusions could you make based on that? So I'm going to go ahead and turn on the voltage. So we can see the cathode ray, this beam of particles. And he would adjust the charge on the plates and see the deflection of that beam. You can see it's always going toward the positive. Okay, so what charge does it have? Is it itself positive or negative if it's being attracted to the negative? Opposites attract. So he concluded that this cathode ray must be made of negatively charged particles. And then he tried messing with the different materials that were creating those rays, okay, using a variety of different metals. And he saw no effect on the ray. The ray stayed the same, no matter what orientation it was in. The material didn't matter. Now, this told J.J. Thompson and his research team that something that was making up the cathode ray was common between all of these different metals. We had discovered part of the atom. We had discovered the electron. He figured out that those cathode rays must be made of small negatively charged particles that are coming from these metallic atoms. And since identical rays are coming from all these different metals, these particles must be in all atoms, okay? And indeed, it is. It's the electron. He discovered the electron. So our new model of the atom consisted of negatively charged electrons sitting in a cloud of positive charged. This is sometimes referred to as the plum pudding model of the atom or the chocolate chip cookie model. But yeah. Also, why does it make sense that we discovered electrons first? Well, they're on the outside of atoms. So if they're on the outside, it makes sense that we discovered them first before we delved into the inner workings of the atom. And how did we do that? That came from someone called Rutherford and his gold foil experiment. You can check out the CK12 article on it. It's really good. I'll link it in the description. But basically what it was is he fired alpha particles, which he knew to be large, positively charged particles, and was firing them at a sheet of gold foil. Now, this is equivalent in his mind to firing a paintball gun at a sheet of tissue paper, okay? The paintballs are not going to be deflected backward from the sheet of tissue paper, okay? They're likely to go right through. That's what the plum pudding, the current model of the atom, would have predicted. But instead, he saw some of these alpha particles being bounced back almost straight towards the detector at crazy angles, okay? Since these positive particles were being deflected, there must be something positive that is repelling it. And since it wasn't happening to all the particles, most of the particles were going straight through. He was like, okay, well, there must be something small but massive and positive in the atoms that is causing that deflection. Okay, since some of these are getting bounced back, but most of them are going through, most of the atom must be able to go through, but there's a small positively charged thing in the middle. And that led to the nuclear model. Thomas Rutherford discovered the nucleus in 1911. And in his new model of the atom, we had a dense positively charged sphere in the center of the atom, the nucleus. And the electrons were still just around that positive nucleus. Yep. And by the way, Thompson won the Nobel Prize, and Rutherford was some of his students, and Niels Bohr, the next scientist we're going to talk about, was also one of his students. So we were developing and learning about the atom in rapid succession. So let's look at what the next big development was. And this had to do with observing atomic and emission spectra. So I'm going to show you guys a demonstration in a minute, and I want you to look at what the difference is between light sources and the gas tubes that we're going to see, the difference between the elements, and what is so special about the hydrogen spectrum. So let's go ahead and look at that. Hey guys, so we're going to be looking at atomic absorption and emission spectra, which was what Niels Bohr was studying when he discovered his model of the atom. But in order to see the atomic absorption and emission spectra, we have to be able to break light into its spectrum. You guys might know that white light, like what's coming from this flashlight right here, is actually made up of all the different colors. And what I have here are some diffraction grating glasses that will split that light up to us. Now, unlike a spectrograph, which does this only in one direction, these glasses are going to split the light in all directions. So we'll try to focus on one just off to one side of it. Okay, let's go ahead and see how this works. Okay, so I probably look a little funny now, but hopefully you can see that rainbow spectrum of light coming from the flashlight. Now, this is called a continuous spectrum because you're seeing the whole gambit from red to blue. This will look different than the gas tubes, which we're going to look at next, okay? So let's go ahead and see. So this is hydrogen, okay? And hopefully you can see that red, blue, and purple light coming off of here. That light is the hydrogen spectrum. Now, this is what Bohr was studying. He was able to map each of those lines of light to actual transitions of the electrons between energy levels and orbits in the atom itself. And he was stoked on this. It was awesome. So then he moved on to helium. Okay. Now, right away, what do you notice about helium spectra compared to hydrogens? Okay? Hopefully you can see there's a lot more colors in the spectrum. Okay? These colors are because there's more electrons. There's electricity running through here, and it's causing the electrons in helium to get excited and move within their atoms, thus emitting the light. And no matter how hard Bohr tried, he couldn't make the math work for helium the way he had for hydrogen. So he had to move on. And now just for fun, let's look at some other elements. You can see that one super bright with a wide variety of red lights there. Neon. So as you saw, the spectrums of the elements are unique to that element. Each element emits and absorbs specific wavelengths of light. And when you have bigger elements, they have a wider range and more wavelengths of light that they can absorb or emit. This is actually how we determine the composition of distant stars and galaxies in the universe. Now, what Niels Bohr was able to do was he was able to show that the electron transitions in hydrogen's atom could be directly mapped mathematically to their position in the nucleus, okay? he was able to tie every single wave of light with an electron moving from one level away from the nucleus to another. And that led to the Bohr model of the atom, the planetary model. In this one, each electron is in an orbit around it. Okay? And each energy level, as he called them, could fit a certain number of electrons, with the first energy level being closest to the nucleus, able to fit 2 electrons, the second 8, the third 18, and the fourth 22. And electrons, when they absorb light, they jump up an energy level, and when they emit light, they go down an energy level. And Bohr was able to create a simple equation that would predict those energies for hydrogen. He was stoked. He was like, score, look at this equation. I can tell where all of the electrons in the atom are just by using this equation and what the light will do to them. So he was like, score, mastered hydrogen, the element, the element with just 1 proton and 1 electron. And then he moved to helium, which has 2 protons and 2 electrons. And the math just didn't work out. He tried and he tried and he tried, and he couldn't get the math to work for the helium atom. So the new model of the atom that is able to predict all of the electrons is called the quantum model. Now, this is tied to Erwin Schrödinger and incorporates principles of wave-particle duality. Now, in this quantum model, electrons are not in a specific location, but rather a wave or cloud of probability. And that probability cloud is described by 4 quantum numbers that describe that relative distance from the nucleus, just like the Bohr model. That's still the principal energy quantum number, the principal way that we describe where electrons are located. And now we go farther and deeper by describing the shape and orientation of the orbital that electron is in, and a property called spin of the electrons, which isn't actually spin, but the quantum world is weird. This model is awesome, and it's been able to lead to some amazing scientific discoveries. But it's also really complicated. So at our level, and in most chemistry classes and courses and studies that we do, Bohr models are sufficient, and we'll use those a lot. But the quantum model goes a little bit deeper and is our current model of the atom, and the one that we are diving in deeper and deeper into as we explore the world of quantum physics. So that's the history of the atom. What I want us to be able to do is really explain how this developed over time and what some of the pros and cons of each of those models are. Okay, cool? Okay, cool.